Okay, this lesson is Chapter 2, Section 2, and the topic is Power Functions with Modeling. What you'll learn about are power functions and variation, monomial functions and their graphs, graphs of power functions, and modeling with power functions. And why you're going to learn this? Power functions specify the proportional relationships of geometry, chemistry, and physics. So what is a power function? Any function that can be written in the form f of x equals k times x to the a power, where k and a are non-zero constants, is a power function. The constant a is the power, and k is the constant of variation, or constant of proportion. We say f of x varies as the eighth power of x, or f of x is proportional to the eighth power of x. An example of analyzing power functions: state the power and constant of variation for the function f of x equals the fourth root of x, and draw the graph of it. Well, anytime we're working with root functions, it's always a good idea to convert that root function to make it look like a power function. And this is going to be especially important when we get to calculus. So if I rewrite f of x as f of x equals x to the 1/4 power in rational exponent form, it's much easier to do the analysis that we're asked to do. So f of x equals the fourth root of x is equivalent to x to the 1/4 power, which is equivalent to 1 times x to the 1/4 power. So the power is 1/4, and the constant of variation is 1. And this is what the graph of x to the 1/4 power, or the fourth root of x, looks like. Most root functions, square root, cube root, fourth root, and so on, have this general shape in their graphs. A monomial function is any function that can be written as f of x equals k, or f of x equals k times x to the n, where k is a constant and n is a positive integer. It's a monomial function. So describe how to obtain the graph of the function f of x equals 3x to the third power from the graph of g of x equals x to the n with the same power n, meaning g of x equals x to the third power. How could we get f of x from g of x? What's different about these two? Well, clearly the difference is the 3 here, the coefficient on x cubed. So how does that change the graph? Well, we obtain the graph of f of x equals 3x to the third by vertically stretching the graph of x cubed by a factor of 3. Both are odd functions. So what it means to vertically stretch is that we're going to multiply the outputs of the function g by 3 to get the outputs of f. So for instance, g of 1 would be 1 cubed, which is 1. Okay? F of 1 is 3 times that value. Okay, and another example, g of 3 would be 27, but f of 3 would be 3 times 27, which is 81. So when you think about what that does to those points, if 1, 1 is here, then 1, 3 could be here. And if 327, this won't be to scale, but if 327 was here, then 381 could be way up here. So you can see if the curve had this general form like this, then we would be doing a stretch this way. So the values of f would be increasing much faster, or decreasing depending on where we're looking. Okay? So graphs of power functions. For any power function f of x equals k times x to the a, one of the following 3 things happens when x is less than 0. F is undefined for x is less than 0, f is an even function, or f is an odd function. So here we have some graphs. Let's take a look at the graph on the left side here, graph A. You see the red curve represents what happens when a is greater than 1, meaning the exponent on x is greater than 1. So we're talking about squared, cubed, fourth power functions. The blue curve, these are our root functions. Okay, x to the 1/2, x to the 1/4, x to the 1/3, square root, cubic root. Okay. A less than 0, these are our reciprocal functions. Okay, so the green curve represents what happens when we have a reciprocal type function. And in this first graph A, we all have a reference point here of 1k, where k is positive as well, right? So k is greater than 0 in these graphs over here. So we're in the first quadrant. Now the opposite of that, if you will, over here in graph B, would be what are these graphs going to look like when k is less than 0? So if we take our reference point 1 comma k, and we have a negative k value here, we're in the fourth quadrant now. And this is what the general shapes of these would look like. So here, the blue curve, we have our fourth root function, cube root function, square root function. If k were negative, this is what the graph would look like. It's a reflection across the x-axis. And you can see here, the red curve is also a reflection across the x-axis of the curve that we had in graph A, as is the green curve. Okay, so by making k negative, okay, a negative coefficient on our power function, we get a reflection across the x-axis. And one thing that I didn't mention in both graphs, if a equals 1, we have a linear function. Okay, x to the first power, that's linear. So in general, an odd function will have this shape, like this, or like this. All right, every odd function. Now, what happens is, the only difference is, at some point along the curve, some interesting things happen. Okay, here we have straight lines, but those are odd functions. Linear functions are odd. All right, but an odd function could also look like this. Okay, could look like this. Could look like this. All right, could look like this. Okay, lots of variations. But in general, if we were to zoom way, way, way far out on the curve, way far out, okay, make our viewing window of our calculator like in the thousands, we are going to see this general linear look to any odd function. Now, an even function is going to have a general U-shaped curve. Again, the difference among them is at some point along the curve, some interesting things happen. So if we think about our most basic U-shaped curve, we have our quadratic function, the parabola. Okay, by the way, parabola is a geometric term. When we talk about the graphical representation of a function, we're talking about geometry. So here's a squared function. Now, what these U-shaped curves could look like is we could have it come down, bounce around a lot, and then come back out this way. Could be coming up with a couple of, remember these are called maxima, and go back down. Okay. These would both be examples, or all four of these really would be examples of even functions. So even functions, even if we zoom way, way out, are going to look like parabolas, parabolic in nature. When we zoom in, we may see some funny things happening where we get a bunch of extrema. Okay, so some quick review here. What I would do with these is I would pause the video. These are just some practice problems for you. I'd pause the video, try these in your notes. When you replay the video, it'll go to the next slide and show you the answers to these solutions. So hopefully you get these right. If you have any questions about any parts of the video or any of these problems, please be prepared to ask those in class. And here are your solutions.